Okay, so the next part is more about convergence. We'll talk about almost sure convergence, strong law of large numbers, and a third type of convergence in distribution. And we'll try to look at some pertinent examples. The reference, again, are the same two books, Wackerle and Casella-Berger, section 9.3 in the first and 5.5 in the next. Okay, so suppose we have a sample, independent sample, y1, y2, ... and y, and they're random variables, or they could be constants, which we can think of also as a degenerate random variable. And we say yn converges as, or almost surely, to y. How do we define that? Well, we say yn, the sequence, converges almost surely to y if for any epsilon greater than 0, the probability that the limit of the difference between yn and y is less than any, so any epsilon, any positive epsilon is 1. In other words, the set of these random quantities on which yn does not go to y or get arbitrarily close to y, maybe is not the null set, but it has no probability. Okay, so that's the idea. Yn converges pointwise to y, except possibly on a set that has no probability. Okay, no chance of occurring in any real sense. Okay, so here I had already started this, so let's do our first example to see how this might work. So suppose u is uniform and we set yn to u plus u to the n. So from this, I build out this entire sequence. Y1, of course, is 2 times u, y2 is u plus u squared, etc. And as you see, the u to the n will get small, except for one case when u is 1. So in fact, the limit as n goes to infinity of this difference here is just equal to 0 if u is less than 1, or 1 if u is equal to 1. And since the probability that u is less than 1 is equal to 1, then yn converges almost surely to u. It doesn't converge to u when u is 1, but that set has no chance, no probability. Okay, the probability u equals 1 is 0. So the definition holds, right? This limit, in fact, is 0 in this case down here. So that this condition is met everywhere except at a single point here, and that has no probability. So this is met, right? Okay. All right, so fine. All right, so let's do our next example, which is, where the hell did it go? Yeah, okay, so, yeah, okay, so for the next examples, a bit more elaborate, we will just define, we'll still let u equal, be uniform, say 0, 1. And now we'll define y1 equal to u plus an indicator function on the set 0, 1 for u. They're all going to look like this. Y2 equals u plus 1, 0, 1/2 of u. So this one means that if u is less than 1/2, this will be 2. If it's greater than 1/2, it will be 1, 3, etc. But we just keep going like this. Y4, but what do I mean? Well, now I'll divide it in thirds like this, etc. So y7 would be 0 to 1/4. What's y6? Y5 y6 would be 2/3 to 1, y7 would be 0 to 1/4, etc. So let's just write ... And let's let y equal, we don't need y, right? Okay, so what we'll show now is that yn converges to u in probability, but not almost surely. Okay, AS. Okay. All right. Okay, what's going on? Well, pick a point. Okay, pick any point in your head that you want. 5/7, say. And you see, so suppose, let's just look at one point. Suppose u equals little u, it's maybe 5/7 or something. Then what sequence do we get? Then we get a y1 equals 2. That's always going to be 2. y2 equals 0. y3 equals 1. y4 equals, oh my god, 1. Oh, sorry, not right. It's not exactly right, is it? Okay, hold on. It's okay. Fix it up here. So let's do a few of these. Yeah, say u equals 5/7. So y1 equals 1 and 5/7, right? So y2 equals 5/7. y3 equals 1 and 5/7. y4 equals 5/7. You get the idea. What about between 1/3 and 2/3? 2/3, 5/7 is no. So y5 is 5/7. What's y6? 1 and 5/7. y7, 5/7, etc. Right? Well, what happens? As n gets bigger, the interval gets smaller and smaller. So we can see why n will converge in probability to u. At every point, it's still not going to converge though. So because the intervals get smaller and smaller, arbitrarily small, it's true that the probability that yn minus u being greater than epsilon, some small epsilon, will be 0, right? In the limit. As the intervals get smaller and smaller. Remember, I haven't taken the limit yet. So if I'm giving you any particular yn and any particular u, the probability that this is greater than epsilon is very small, because as we go on and on, the chance that you will be in this special interval is going to get smaller and smaller. So this is getting smaller and smaller as n gets bigger and bigger. And in the limit, this will be 0. So that's right, gets arbitrarily small, and the limit n to infinity of this is equal to 0. So yn does converge to u in probability. However, what is yn minus u is equal to? Well, it depends. It's either 0 or 1. And this just depends on n and u. So does this, right? But the limit doesn't exist, right? The limit n to infinity of yn minus u does not exist for any u, right? If u is any number, it doesn't matter because I will get infinitely many ones and infinitely many zeros. So the limit can't exist. Now, as we go on, right? As you go on, you get bigger and bigger n. You're going to have many, many more zeros. You know, you have all zeros. Then, oh, there's the special interval. Now I get a 1 for this, right? For the difference here. And then even more zeros, right? The number of zeros between each one is increasing each time, but it's easy to see. There's no reason this would ever stop. It's just going to keep going. You're going to get another 1 eventually, and you just get more and more time before you get that 1. So therefore, the probability that the limit n to infinity of yn minus u is less than epsilon is going to be equal to 0, not 1. It needs to be 1 for almost sure, for any epsilon small, less than or equal to 1. So yn does not converge to u as. You can write the as over there. Okay. Well, here's a for an application of it is in the strong law of large numbers. So the theorem says that let y1 iid with EYI equal mu, and variance YI equals sigma squared finite. Then yn bar, the nth sample mean of y1 through yn, converges to mu almost surely. This is called strong law large numbers. Okay, let's look at an example before, and we can talk about what this means in the example. So suppose I have y1, y2, iid Bernoulli, let's just make it 1/2, but we could put any p we want in here, other than 0 and 1, I guess. And yes, and so the theorem says, so SLLN says yn bar goes to 1/2, right? As. Okay, what does this mean? This means except at a set of measure 0 of no probability, this will be true. Asymptotically, if I take the average of the ones and zeros, I will have half ones and half zeros. Starting to seem a little wild, isn't it? This is not something I intend to explain, or can I prove now? It takes a bit of work to do this, but this is what the theorem says, and I can't claim there's any sort of easy intuition for this. But this is so. So let's think about what is the sample space here that you would be talking about the measure. So the sample space is actually uncountable. It's the set of all, is the set of all possible sequences of ones and zeros, right? Now, not all of these sequences will have a yn bar that converges to 1/2. We'll have an equal number of ones and zeros, but only the ones that do asymptotically have that have any measure to them, have any probability. If you take out the ones that don't do this, there's zero probability of those occurring. So, not every, so let's write some sequences do not satisfy yn bar goes to 1/2. For example, and it really here I should write it maybe like a lowercase thing, just so you know, I'm just talking about the actual numbered sequences now. For example, and in fact, yeah, you need the arrow here too, because you're not stopping, so you're going forever. So for example, if yi equals 0 for all I, then clearly yn bar goes to 0. So, and same thing, you could go like this sequence, like yi equal 1, yn bar goes to 1, not 1/2. What if you had y1, y2 equal 1, y3 equal 0, y4 equal 1? I know I could express this as a pattern, but I don't want to try right now. If I have something like this where every third one is 0 and the others, then yn bar would approach 2/3. But if I take the aggregate, the union of all of these sequences, the probability of that union is still 0. So in other words, if we partition into n and nc, where sequence S in n satisfies, means that y, okay, and otherwise, I should make the arrow here, and S in nc then you will find okay. So I'm not saying I'm proving this, but this is true. Okay. So what this tells you is, yeah, every sequence that has a probability, yeah, I'm not trying to say it and break it down to easier language. It will not make sense if I try it now. So I think if you have questions, we can talk about it. All right. The last type of convergence we'll talk about in the course is in distribution. So suppose I have y1, y2, and suppose we have and y, and these are RVs. Now we probably really want them to be RVs. Then yn converges to y in distribution if the probability that yn is less than or equal to y goes to the probability that y is less than or equal to y, at least at all y's where this is continuous. So the CDFs converge. Okay, and I'm just writing a regular arrow to mean the limit as n goes to infinity. So as n goes to infinity, these are the same. Another way to write this is to just write the CDFs converge, and it is important that this probability be continuous at little y. So I don't want to have a jump at little y. Okay, so if the random variables are continuous random variables, this won't be a problem. And even if they're not continuous, it might, yeah, it would be a problem sometimes. So, or if it's mixed or something else, it could be a problem. All right, so just take that. I won't even write this down. Maybe we should write this down. Let's just say at all y for which this CDF is continuous. Okay, example. Suppose we have y1, y2, IID uniform again, 0, 1. And let's show that A, as a little warm up, that the nth biggest out of n, so yn equal to the max of, this doesn't really mean out of a number bigger than n, it means the max of y1 to yn. So the max of the first, so y parentheses 1 would be y1, y parentheses 2 would be the max of y1, y2, y parentheses 3 would be the max of y1, y2, y3. Okay, and then b, so this converges in probability to 1. And b, if I take n and multiply 1 minus this, which should go to 0. So I have an indeterminate form, infinity times 0. This converges in distribution to an exponential, and you could just cheat and just write the description of the distribution, an exponential random variable with mean or rate equal to 1. Okay, can we show this? Yes, we should be able to show this. To do the first one, so for A, let's see, probability, let's see, what do we have to show? We have to show the probability that, yeah, we have to deal with the probability that yn minus 1 is greater than epsilon, right? But this, what is this equal to? This is equal to the probability, we know yn is less than 1, right? So this is the probability 1 minus yn is, this is the probability 1 minus yn, let's see, this probability 1 minus yn is greater than epsilon. So I could get rid of that at least. And this is just equal to the probability that yn is less than 1 minus epsilon, I think, right? Yes. And what's the probability yn is less than this? So this is a number less than 1. All of them have to be, right? And since it's uniform, this is 1 minus epsilon to the n. And this goes to 0, right? So this goes to 0 as n goes to, so yn converges to 1 in probability. Now, what about the other piece to do the convergence and distribution? Compute the CDF. Okay, so for B, let's consider n 1 minus yn, and let's look at the probability, say that this is less than or equal to little y, say. Okay, let's look at this. All right. Again, I think I want to get the yn free, so let's write, this is the probability 1 minus yn. is less than or equal to y over n, which is equal to the probability yn is greater than or equal to, add and subtract 1 minus y over n. Well, since I'm dealing with a max, I really want the less than, so this is equal to 1 minus the probability yn is less than or equal to 1 minus y over n, where I'm ignoring the equality because this is a continuous random variable. Okay, the probability the max is less than this, they all need to be less than this. So this is equal to 1 minus 1 minus y over n to the nth power, right? Okay, all right, so we have this. And then for convergence in distribution, I need to see what this goes to in the limit. If I take the limit as n goes to infinity, this quantity is equal to e to the minus y. So limit n to infinity, probability n 1 minus yn less than y is equal to 1 minus e to the minus y, which is the or exponential 1 RV. So we have shown that if you take this strange function of this yn, it does converge to an exponential 1 random variable. It has the same distribution. Okay, this is cute, but let's see maybe how this is also very useful. So recall the central limit theorem, which says if y1, y2 are iid with e yi equal mu, variance yi equals sigma squared, finite, let's say they're both finite, then the central limit theorem says yn bar, the mean, sample mean, minus mu over, this is really what it says, the CDF converges to a standard normal. I'm writing it this way, that's fine. You could also write arrow distribution to z, normal 0, 1. It's more or less interchangeable how you want to write it, I think. So we have a theorem for this, which we will not prove this, that if yn converges in distribution to y and xn and y should be random, probably, xn converges in distribution to, well, I only really need the constant here. This could be a random variable though. But say xn converges in probability to c, well then x and yn converges in distribution to cy, and xn plus yn converges in distribution to c plus y. This is known as Slutsky's theorem. Okay, so theorem Slutskova, and but you don't need to know that. You just need to know what it says. And let's see, running out of paper, so let's just get one more. Okay, and Yes, okay, so this is a theorem, okay? I can combine these two. So let's see how this might work in two short examples. So suppose we label Tn equal Z over the square root of, let's call this Xn over N, where Xn is equal to chi squared with n degrees of freedom, and Z normal 0, 1, and these are independent. Okay, well, Xn over N converges in probability to 1. Why? This is because Xn is equal to the sum of independent standard normals. And so each of these has mean, these are independent, and Zi, Iid, normal 0, 1, each has mean 1. So Xn has mean n, so this has mean 1. And so using the theorem of Slutsky, we have Tn converges in distribution to, well, look, this is going in probability to 1. So it's just the product rule, right? So converges in distribution to Z over 1, or you could have, 1 over 1 times Z normal 0, 1. So this shows that the T distribution converges to the standard normal as the degrees of freedom increase to infinity. Here's another one, kind of interesting. If the sample variance of a random sample, let's write this as a fact. Suppose we have y1, y2, iid, and say EYI mu. Let's just make them finite. And suppose Sn squared goes to, the variance of Sn squared goes to 0, so then we know Sn converges in probability to sigma. Well, then we could take the estimated function of this, y bar n minus mu over Sn over square root of n. And notice that we could write this like y bar n minus mu over sigma over square root n times sigma over Sn. And because Sn goes to sigma, then this follows from the limit laws for convergence in probability. This goes to 1. And from the central limit theorem, you almost don't have to write this when you're writing it like this, because what else could it mean? Okay, and the central limit theorem says this goes to standard normal, this goes to 1, so the whole thing also goes to standard normal. So in other words, as long as the sample variance is consistent for your sample, for your distribution, then this is a consistent estimator for mu, and it will also satisfy the central limit theorem. It also approaches the standard normal. Okay, so this, you could put distribution, but it's clear, really, has to be, right? That's what it has to mean. Okay, that's all. Thanks. I think that was probably a lot longer than I thought, but thank you. The next lecture 11 is on sufficiency.